All right, folks, happy Wednesday. Um, we are in our last day of lecture. Tomorrow you do have your final exam, and then that is due by Friday at 9:30 a.m. as well as your quiz 15, and then quiz 16 if you choose to do the quiz 16. So remember, quiz 16 is optional. You do not need to do that, but it can replace your lowest quiz grade if that is something that you think would help you out. All right, so let's go ahead and get started. We're going to get started with 11.7 today. So that's sort of the last section that we're going to be covering in Calc 2. And we're going to be taking a look at the power series again, but we're going to start to look at some of the applications of it. But remember, this is all very, very introductory, and it's really only going to be important for those of you who might be moving on to become math majors, okay? So I'm going to go ahead and share my screen. All right, so we are in 11.7, which is called power series representation of functions, okay? So let's start off with what we know. So what we know is that an infinite geometric series converges under certain circumstances, specifically if the common ratio, that's our R value, if our common ratio, not only is it less than 1, but the absolute value of that common ratio has to be less than 1, okay? So we're looking at that absolute value of common ratio is less than 1. We're going to end up with a convergent geometric series. But if we have a common ratio greater than 1, that absolute value being greater than 1, then we're going to get a geometric series that diverges, okay? And we also know that we can write sort of the general form of an infinite geometric series with a r to the n. And so remember, a is kind of like your starting term, n is the power that the ratio gets raised to. And if it is convergent, right? If your infinite series is convergent, then you can use this formula a over 1 minus r to help you find the sum of that particular series, okay? Now, what's new? Power series can actually be used to represent a whole bunch of functions, okay? So we kind of talked about it yesterday, how power series are actually how your calculator finds values for e to a power or natural log to a power, but it can also be used to approximate a lot of different values. For example, it could be used to approximate values of a quadratic or a polynomial of any degree, really. So cubic, fourth degree, fifth degree, but we can use it to approximate a bunch of different values. But what we're going to focus on today is sort of keeping in line with what we talked about yesterday about having a power series, having a radius of convergence and an interval of convergence. So we're still going to be finding those today, but what we're going to do now is see how we can write a function using what we call power series representation, okay? So we're going to take the way that we write functions and we're going to find a different way to write them, specifically using the power series. And what that's going to allow us to do at some point in the future, not here, is to approximate values, to find different ways of finding integrals and derivatives. And we're just going to sort of cover the surface of that today, okay? So let's get started with Roman numeral 1, the power series representation. So yesterday we saw that a power series representation in general is the summation, and we usually start with 0 and we go to infinity of there's some constant that sort of changes for every single term, and then we had the x minus a to the n. Okay, now more simply, what we're going to do right now is sort of assume that the center point is at 0. Okay, or rather, the value that this power series converges to all of the time is 0. And so what that's going to give us is we can actually keep this c sub n, but the a is going to go ahead and go away. And so we'll just have x to the n. Okay, so we're just sort of assuming a very special case where we're looking at things that are centered around 0. Now, one thing that we didn't do yesterday, or we did a little bit, is we sort of expanded this. We said, what happens if we plug in the values for n? What happens if we plug in 0? What happens if we plug in 1? What happens if we plug in 2? Because like any series, a series is simply each individual term, but added up all together. So if I were to plug in 0, or rather find a sub 0, what would that give us?
Just 0.
Sorry, say that again?
Zero.
No, it's not going to be 0.
C sub 0?
C sub 0, yeah, because we plug in a 0 there. And then what happens when we plug in x, a 0 in for the x?
1. Oh, 0.
Well, we're going to have x to the 0 power, right? If we just like say, let's plug in 0. Now, what happens if we plug in 1?
C sub 1 times x.
And then we could keep plugging in numbers like c sub 2 x squared. Now, let's say I stopped here for a moment. Instead of saying, oh, let's find an infinite series, I said, let's truncate it. Let's stop after n equals 2. What kind of function is this? Yeah, this is a quadratic function, right? So when we're looking at these series with the power series, a lot of times we actually don't go all the way to infinity, but rather we can use the first few terms to model a given sequence or series. So right here we have a quadratic one. If I were to keep adding like the n equals 3, if I were to truncate it there, I would end up with a cubic function, okay? Now, if we were to say, hey, let's skip a few and just have our c sub n x to the n, that would be like any random term. And then because of this particular example is an infinite one, we would say it keeps going forever and ever, okay? So what this allows us to do is if we said, hey, let's truncate it just for the first 3 terms, we would end up being able to approximate some sort of quadratic. Okay, so sometimes that's useful. If we said, hey, let's go ahead and just take the first 4 terms, we would be able to model some sort of cubic function, okay? And you can see that the more terms we add, the larger the polynomial we can model. And so what this allows us to do is, let's go back down here. It enables us to find functional values in a new way. So instead of saying, okay, I'm going to use an XY table for my quadratic or my cubic, maybe you can plug values into your power series representation and then just say, I'm only going to go until the power is 2, or I'm only going to go until the power is 3. Okay, so this is sort of a different way of finding values of a function. So we're going to take a look at really more the second part today, which is that we're going to be able to solve problems using differentiation and integration with new techniques. Okay, so we kind of talked about this yesterday, or kind of hinted at it, that as much as we've spent some time studying calculus, right, we're sort of like in the 2/3 of the way through your calculus experience, when you get to the world of math beyond calculus, there are actually other ways to approach problems that involve derivatives and integrals rather than just derivatives and integrals, okay? And so we're just going to sort of set the stage for like how that might look in the future. All right, so what I'd like to do here is take some time and take a look at this first example, right? So I've got this infinite series n equals 0 to infinity of a times r to the n. And that's something that we recognize, hopefully, as a geometric series, right? This is an infinite geometric series. And earlier I said that this, if it converges, I could say that the sum is a over 1 minus r, right? And we also had a caveat that the ratio, the absolute value of the ratio, needed to be less than 1 in order for this to be true, okay? But let's think for a moment what we know about equations, right? Because what we have here is really an equation. So this second side, yes, it represents the sum of a convergent geometric series, but it's also a way to represent the series. It's another way to represent the series, okay? Now, to be specific, it's another way to represent a geometric series, all right? But we're going to take a look at how we can use this to sort of generalize the idea of a power function, power series representation, okay? So let's go back to this original. And what I'd like us to do is we're going to let a equal 1 and r equals x. All right, so we're going to take only the series part and we're going to say, let's let a equal 1 and r equals x. That's going to give us the sum from n equals 0 to infinity of not a, but 1, and not r, but x to the power of n. Do those substitutions make sense?
Yes.
Yeah, okay. So if I asked you to simplify what I wrote here, what would we sort of leave out?
1.
Leave the 1 out, right? I think it was a long time ago in our mathematic careers that we decided if the coefficient's 1, we don't really need to write it, okay? So for that reason, we can sort of simplify and say, I don't need to write the 1. But what I'd like us to do now, so we've sort of filled in the information on this left-hand side of the equal sign, but I'd like us to fill in the right-hand side of the equal sign. So where I have a over 1 minus r, what's another way that I can write that if I let a equal 1 and r equal x?
1 over 1 minus x.
1, because a is 1, over 1 minus not r, but x. Yeah, exactly. So with these substitutions, we're able to rewrite something that we know is true, okay? Now, let's not forget about this part. We said if our common ratio is less than 1, we want to say if the absolute value of x is less than 1. Okay. All right. So here's what all of this means, right? So all we've done is a simple substitution. We've said a is 1 and r equals x. And then we were able to get this expression right here. Okay. So let's maybe unpack in words what we found. So what we found is this. We can represent, if I had a function that was 1 over 1 minus x, okay, I can represent that with the power series representation of what? What is that power series representation that I can write 1 over 1 minus x as?
Lambda of x to the n.
Sorry, say that again?
X to the n.
You're gonna have the whole thing though. It's not just x to the n, you need like the sigma notation also, okay? So you need this part, and that part, and that x to the n. All right, so if we see a function 1 over 1 minus x, another way that we can represent that is the infinite series x to the n, or the power series x to the n. But what's also important is that we include if absolute value of x is less than 1. Using some vocabulary from yesterday, what does that 1 represent?
Your L value?
I could see how you think it's an L value, but we've already isolated the absolute value. So what's a maybe more specific term?
Radius?
Yeah, this is actually our radius of convergence. Okay, so when we look at a bunch of functions, all right, so today we're going to be looking at a lot of functions that kind of look like this, all right? And our job is going to be to rewrite them in some sort of power series representation, meaning we're getting a function, but we want to write it as an infinite series. And because we're going to be writing it as an infinite series, we want to make sure we also have our radius of convergence, okay? So and that's sort of what we're going to be doing today, all right? We're going to start with a function. We're going to try and make it look like a power series, but this right here is going to help us get started with a lot of these problems. All right, so this sigma of n equals 0 to infinity of x to the n equals 1 over 1 minus x. We're going to be using that along with the idea of substitution to help us figure out the power series representation of a few different types of function. Okay. All right. Any questions on example number 1 so far? Okay, so let's try it out. So example number 2 says find a power series representation for f of x equals 1 over 1 plus x cubed, and we're going to determine that interval of convergence. So before we start that one, let me just rewrite what we had above, which is the sum from n equals 0. I'm going to write it the other way. 1 over 1 minus x, we said was equivalent to the sum from n equals 0 to infinity of x to the power of n. So if we maybe color-coded this a little bit, we might be able to see that if I have a 1 minus x on the bottom, that then I just take that x and I raise it to the power of n. Does that kind of make sense to us? Like if I have 1 over 1 minus something, then the way I write it as a power series representation is I take that something and I raise it to the power of n. And we want to make sure we also have that x is less than 1. Okay. So we start off with this function here. We have f of x equals 1 over 1 plus x cubed, all right? And you might be like, well, this looks way different than what we had before. This one has the cube and the other one totally didn't. So I don't understand how we're supposed to make a connection here. But let's think about it again in more of a zoomed out view, meaning I had 1 over something. And so far I look at this, I've got 1 over something. And then I have, so this part is the same as that part, right? And this part is the same as this part. So if only I could change the denominator to be 1 minus something instead of 1 plus something, my life would be much easier, because then I can just do a substitution, okay? So how can I write this expression to be 1 over 1 minus something? Like, what does that something become?
X times x squared. I mean negative x squared.
Negative x cubed.
Yeah, negative x, not squared, but cubed. Right?
Well, I was thinking like minus x and then distribute that to negative x squared. But
What are you talking about?
She had it.
like negative x times negative x squared, I thought, but never mind.
All right, so let's maybe think a little bit simpler, right? I don't necessarily want to split terms yet, because if I split terms, I'm going to make more things than I need to. But the only thing I need to match right now is sort of a 1 minus on the bottom, right? And the easiest way to do that, you've got your 1 here and your minus sign now. That matches too. And now you have your, what was our x before is now negative x cubed. Does that make sense?
Yes.
Maybe. Okay. So once we've created something that looks extremely similar to what we know, which is 1 over 1 minus something, okay? Then what we can do is substitute everywhere we see that x in that original example we did, we're now going to replace that with negative x cubed, okay? But here's the deal. We want to replace it not just in the infinite series, but also in our radius of convergence. So I'm going to write my sigma. I'm going to have n equals 0 on the bottom, infinity on the top. I've got x, but instead of x, I'm going to write negative x cubed, and then the power of n. Okay. So all I've done is substitute. But I also want to substitute here. So I have negative x cubed is still going to be less than 1. All right. We've done what I think is sort of the hard part, which is where we manipulate our function to match what we had earlier with the geometric function, okay? Beyond this, we typically just kind of split things so that we have, especially when we have a negative sign like this and we're raising to a power, we kind of know this is going to be an alternating series. So we really want to pull that -1 to the n power out, okay? And so when we have something like this, we can split this into -1 to the n, and then x to the 3n. Okay. And we can also say here that if negative x cubed, if I want the absolute value of that, I really only have the absolute value of x, and I'm going to cube it, and that has to be less than 1, okay? But I want to isolate the absolute value, so I have to take the cube root of both sides. That means that we're going to end up with this as our power series, and I've taken the cube root of both sides, so this is my interval of convergence, or I could write it as like -1 to x to 1. Like both of those would be okay. So for the scope of what we're going to be covering, I'd like us to think about this more as sort of a matching game. Like, how can you make something new look like something that you know? All right. So it might involve changing some signs here, like changing a positive into a negative minus combination. That could be part of it. And we're also going to look at what happens when we layer on different pieces to that, like maybe a multiplication or something like that, okay? So let me pause for a moment. We kind of take a look at example 1 and example 2 on the same page. Are there any questions so far on example 1 and example 2?
Professor, for example 2, it's when you made the bounds or the range, it's -1. It's in between -1 and 1 because of the -1 in the interval of convergence, or is it only because you took off the absolute value?
It's because I took out the absolute value.
Okay, thank you.
You're welcome. And to that point, I think every textbook and every instructor is a little different. So some people might be fine if you just say, I know my radius or my interval of convergence is absolute value of x is less than 1. Like that's the same thing as saying -1 and 1, like it's between those. So either version is totally fine.
Can I ask a quick clarifying question?
Sure.
The -1 and the 1, we won't be testing those points just because if you do that, then you'll have an undefined. in the function?
I think right now we're focused more on the like the power series representation. Like we're more focused on this part of it.
Gotcha.
Does that make sense?
Yeah.
So yes, to be like more exact, we would have to go back and test all those points. But I think for the scope of this class, let's just say, you know, this is how you could find it. Know that you may have to test your endpoints, but let's focus more on the substitution piece.
Cool.
All right. So let's take a look now at example number 3, okay? So again, this is something I want us to kind of see as a game of like what matches with our initial geometric representation, but also what matches with things that we've seen before, okay? So in this case, what's the difference between example 2 and example 3?
Example 3 is going to have an A value.
Tell me what you mean by an A value.
Before, when we substituted 1 for A, and right now we're going to substitute 2x squared for A. And after the representation, I'm pretty sure you're going to have to multiply that back in.
Yeah. So the difference here, right, if we can kind of highlight this, is that we had a 1 in the numerator for both example 1 and example 2, but now we have something else in the numerator, 2x squared, okay? And if we kind of sneak ahead and look at number 4, we can see that there's also some sort of numerator there, okay? So examples 3 and 4 are going to help us find, like, what do we do when we have a numerator that's not 1, all right? And so let's start with this example right here, okay? So I'm going to say that we take our f of x, right? And instead of writing it the way that it's in the problem as one single fraction, we're actually going to split this into 2 pieces. Our numerator, 2x squared, and then times 1 over 1 plus x cubed, right? So that's a valid thing that we can do, because when we're multiplying fractions into a single fraction, we can also similarly split them into multiple fractions, okay? So here's what this is going to give us. We know already from the last example that 1 over 1 plus x cubed can be written as this, right? We already found that out from the last one. So we're not going to do that part again. We're just going to substitute, all right? So I'm going to write this as 2x squared, which stays because I don't know what to do with that yet. But everywhere I see this 1 over 1 plus x cubed, I'm going to write it in its power series representation. Okay, and I'm going to include my interval of convergence. So again, all I've done is kind of split the fraction and then take my work from the previous question and substitute it into here, okay? Now, what we're going to do is we are going to take this 2x squared and we're going to sort of distribute it back into the series, okay? Because yesterday we were like taking the x's out of the series. Today we're putting them back into the series, okay? And so when we put back in the 2x squared, here's what happened. The 2 is going to stay 2, right? This -1 to the n is going to stay. But when I take, you know, yesterday when I was planning this, I was like, oh, I'm so grateful for all the highlighting that I can do, because you can't really highlight on a board in a classroom. but you can highlight on this. But then I was like, now I have so many colors, and I don't know what to do. But okay, so if I combine the x squared with the x to the 3n, how can I write that as a single term?
5n.
No, I cannot write it like that, actually.
X to the 3n plus 2.
Yes, x to the 3n plus 2. So the only way I could combine those if I had an n on both of those, or it was just a 3 and just a 2, then I could combine them, right? But 3n and 2 are not like terms, so I have to kind of leave them separate. Okay. Now, this part doesn't actually change because all I've done is just sort of distribute it back in, okay? So what I have here in example 3, is that this is a power series representation for the 2x squared over 1 plus x cubed, okay? So you can see that they're kind of similar, but that numerator, kind of like James was saying, you have to like multiply it in at some point, okay? So what we did here was we sort of unpacked it so we could use something we knew, and then we put the 2x squared back in so that we were able to, instead of doing this all as like one big problem, kind of chunk it into a smaller problem and then just like a multiplication distribution problem, okay? Okay, so that's example 2 and example 3. So now we're going to take a look at example 4, okay? So we can see from example 4 that we've got a numerator that's not 1. And so our first step is going to be just like example 3, where we kind of pull out that x, split it into a separate fraction. So we'll have x times 1 over 5 minus x. F of x equals the numerator times 1 over 5 minus x. Okay. Now, in thinking back to our example number 1, we wanted to make it look like 1 over 1 minus something. Right? That's what we were trying to match it with, because that's what we knew how to deal with. So how can we modify what we have here so that, well, not the whole thing, but the thing in the parentheses, so that I get 1 over 1 minus something, not 1 over 5 minus something?
Take 1/5 out.
Yeah, we could pull a 5 out all the way, and then we would have a 1 in the place where there's a 5. Very good. Okay, so if we follow that, we're going to get in the front x over 5. Okay. And then I'm going to have my 1 here. And then I'm going to have 1 minus x over 5. Right? Because I had to take the 1/5 out of every single term. Okay, so now this part matches super well with something I already know, okay? So we can write that second part in its power series representation, and then we can take our term in the front and multiply it back in, okay? So let's see what that gives us. We're going to keep the x over 5 in the front. Instead of 1 over 1 minus something, I'm going to write it as the sum of that something to the power of n. So that's going to give me the sum of n equals 0 to infinity of x minus 5 to the power of n. Okay. Now before, when we were writing this, we also considered that interval of convergence, right? So this time, what's inside my absolute value that I'm saying is less than 1?
X over 5.
Yeah, we're taking that x over 5. Exactly, because that was, what color did I use? That was the 1 minus something. That was our something. That was our something. And so we have the absolute value of that something has to be less than 1. Okay. Now, we need to put back in the x over 5. We need to get that back into the power series in order to have a power series that represents the entire function, x over 5 minus x. Okay. And so when we do that, let's go ahead and we're going to bump the 5 back in, and that's going to go in the denominator. And then we're going to bump the x back in, that's going to go in the numerator. And so I'm going to have x on the top and 5 on the bottom. But what is the power going to be now?
N plus 1.
Yeah, we have the n from before, and then we have the 1 from the extra x that got bumped in and the extra 5 that got bumped in. So to the power of n plus 1, okay? Now, to finish off with our interval of convergence, we want to get rid of the 5 in there, okay? So we could factor the 1/5 out, and then we multiply both sides by the 5. That means that our interval of convergence is actually, the absolute value of x has to be less than 5, okay? Now, I bet you can kind of tell why x has to be less than 5. What happens if x is like 6 or 7?
It's greater than 1.
What's greater than 1?
The numerator.
Well, even if the numerator is 4, 4 is greater than 1.
But it being over 5, it would be over more than 1.
So the fraction.
Yes.
Okay, so the fraction is greater than 1. All right, and what happens when a fraction is greater than 1?
Your series will diverge.
Yeah, because remember, this is a geometric series, right? So if our fraction, right, this whole thing right here, if this is greater than 1, we got a big problem because we don't have anything that's going to converge. That is a geometric series that's going to diverge, okay? So that's something that, like, even though we're doing these more complicated applications here, we still have this idea that if it's geometric and it's going to converge, we need to make sure that common ratio is less than 1, okay? And so what we have here is our power series representation along with the interval of convergence for the function x over 5 minus x, okay? All right, so this seems like a good time to take a break, all right? So it is about 10:15 right now. Let's be back at 10:25, and then we'll finish off with derivatives of power series and integrals of power series. And we're not going to get too far into it. I just want us to really think about the power rule and how that applies to like a whole series, okay? So I'll see you back here in about 10 minutes.
Professor, could you scroll? Sorry, never mind.
What did you need?
I just wanted you to scroll up real quick because I missed something on your notes.
I have a question for quiz 16. Are you gonna open it today or tomorrow, or when will quiz 16 be open?
Most of the questions are already up.
Oh, they are? Okay, because I checked yesterday and the quiz wasn't open yet, but thank you.
Okay. Is
Could
this
I see example 2, Professor? Got it. Thank you.
okay, cool. All right, folks, we are going to resume our lesson on 11.7, which is power series representation of functions. And again, in the second half of class, we're going to be focused on what it looks like to maybe take a derivative of a power series and what it looks like to take the integral of a power series, okay? All right. So one of the applications of power series is that sometimes it can be easier to, instead of having to take a derivative of a bazillion different terms, if we could have a pattern that we could just use to take the derivative of an entire series, then it actually saves us quite a bit of work, okay? So let's start by writing our power series representation from earlier, okay? So we said yesterday that a function could be represented as a power series. And we're going to use the one with the a in the term, okay? So we had c sub n x minus a to the power of n. And we were able to take that and say, well, what if we plugged in 0? What if we plugged in 1? What if we plugged in 2? And we kind of kept going from there, okay? So when we plugged in 0, we knew that we get c sub 0, but that x to minus a to the 0 went to 1, so we didn't need to write that part. And then when we plugged in 1, we got c sub 1 x minus a to the power of 1. And then we plugged in 2, and then we plugged in 3, and then we could kind of keep going, okay? Now, in general from here, if I wanted to go about this the long way, and I said, hey, here's a function, take a derivative of it, you would have to find the derivative of this term, this one, this one, this one, and every other term in the entire series. You would have to find the derivative of every single one, okay? So if you had 3 terms, oh, that's not so bad, right? Or you have 4 terms, that's fine. But if you had like 100 terms or 200 terms or even 1,000 terms, that would be a lot of things to take a derivative of, okay? So what we're going to do here is we're going to practice taking the derivative of each one, and then we're going to see if we can come up with sort of a generalized formula for that, all right? So let's say I want to take the derivative of my function. I know I can write that as f prime of x. And what that would mean is I need to take the derivative of this, which I can write as d dx of this power series. Okay? So in general, before we get to the rule, I know that I can write it as just the derivative of the series that I want. And so let's go term by term. How do I, when I take a derivative of c sub 0, what do I get?
0.
I get 0, yeah. So what's the best way to do this? This derivative gave me 0. Okay. What if I take the derivative of, oh gosh, what if I take the derivative of c sub 1 x minus a to the 1? What do I get?
1.
No, I don't get 1.
X minus A.
Nope, I don't get x minus a.
C sub
C.
1.
Yeah.
All right, how are we getting c sub 1? If I take this derivative, I have my constant. Constant multiple rule says I keep the constant where it is. And then I would bring down the power, which is 1, keep my expression, and then 1 minus 1, right? That's what we do with the power rule. And so if I clean this up a little bit, I'm going to get c sub 1 times 1, or I can just write it as c sub 1. So the derivative of this second term becomes c sub 1. Without too much simplifying here, how could I find the derivative of c sub 2 x minus a squared?
2c sub 2 times x minus a.
Okay, x minus a to what power?
That would 1.
To 1, right? Because 2 minus 1, it's power rule. I just lose a power. So we know that that power is 1, okay? Let's do one more just for funsies. If I take the derivative of c sub 3 x minus a to the third power, what do I get?
3 c sub 2 x minus a squared.
Yeah. Right? So every time I take that derivative, I bring the power down, I keep the constant, and then I lose a power there, okay? And so what we can say then, let's go ahead and shrink this a little bit. So what we can say then is that in general, the derivative of a power function is going to be this. I have my power, right? Any power is n, so I bring the power down to the front, times the constant that was already there, times x minus a, but I have to lose a power. Okay. So the n comes from the power that came down. For example, this is n, and look what I have as the coefficient in that term. This is a different n. Look at what I have as the coefficient for that term, okay? So that's where this n comes from. The constant was already there. So this constant, this constant, this constant, those were already there. And I have to keep them there because of the constant multiple rule. And then this n minus 1 came from 3 minus 1 gives me 2. 2 minus 1 gives me 1. 1 minus 1 gives me 0. So there are all these powers, but they're all 1 less than the power in the original, okay? So this is a formula that I can use as sort of like the general formula for taking a derivative. Rather than having to find the derivative of every single term, I can just say, hey, I know it's always going to follow this pattern. But my question to you is, what is the index on the bottom going to be? Because I know it's still going to go to infinity, because we're talking about infinite series here. But what is my n value going to start with here?
1.
And how do you know that it's 1?
Because the exponent n minus 1, it can be a 0, but it can't be a negative number.
Okay, so if we plug in a value for n, it has to make that exponent no less than 0. Okay,
Yeah.
But also, how could you tell from here?
It starts with 0.
Yeah, but we don't ever really write 0. Right? If I have 0 plus something, I don't usually write that. So what's the first official term in this series?
C sub 1.
C sub 1, if that's the first term, I got to start with n equals 1. Okay? So there's a lot of different ways here we can tell sort of what that becomes on the bottom, but this is how we can kind of see something called an index shift, okay? So if you do have differential equations in your future, this idea of an index shift, like moving the bottom number and how that changes the power, is actually a really important skill, okay? Okay, so this is just the first derivative, but I want us to kind of push ourselves a little bit here and say, how can we create a pattern for the second derivative? And maybe even for the third derivative based off of what we know about powers, okay? So let's say I wanted to find the second derivative, okay? I know it's gonna end up being an infinite sum. I know I can put infinity on the top. What is my index going to be on the bottom?
N equals 2.
N equals 2, exactly, because when I take that second derivative, the first two terms are going to go away. There's no c sub 0, there's no c sub 1. My first one is c sub 2, okay? Now, if I take a derivative of this, okay, what parts are going to stay? Like, is that n going to still be there?
It's going to equal 0.
Why does n equal 0?
Well, the exponent will, so it'll equal 1.
Will it stay?
Will your n jump up to an n squared?
Okay, so n is a number, right? N is a number, just like c is a number. So n and c sub n, these two, they're both constants. If I have a constant and I'm taking a derivative, those constants stay where they are. Kind of like my c sub 1 stayed, my c sub 2 stayed. This n and the c sub n, those stay because it's a constant multiple. Okay. But if I'm using the power rule, what else becomes part of the coefficients in the front?
N minus 2.
Not n minus 2, no.
Your n minus 1?
Minus.
That's right.
Yeah, our power, which is n minus 1, comes down as the coefficient. That's the definition of the power rule. Okay. Now my x minus a, that part stays, but what is my new exponent after I've used the power rule?
And minus 2.
Yeah, and minus 2, because I lose another power, okay? So this is a definition of a power series if I were looking for the second derivative, okay? We've got a bunch of constants in the front. These are all constant. I know they're all letters right now, but we need to be able to start to think about letters as constants, knowing what's a constant and what's a variable, okay? And then I just lost one more from the power. So instead of n minus 1, it became n minus 2 because I lost another power. So let's extend this one more time. And what happens if we look for the third derivative? Okay, I want you to take a moment, kind of write out what you think it might be, and then let's share out some ideas on that third derivative. All right. So who can tell me what my bottom and top index are for this particular power series?
3 to infinity.
N equals 3 to infinity. Good. Okay. Now, can I get someone else to tell me what the constants are that are going to be part of this power series?
N times C sub n times n minus 1 times n minus 2
Very
times
nice.
a to the n minus 3.
Okay, just the constants. Just the
Oh,
constants. Okay. Where did you get that n minus 2 from?
It's powered to x minus a, so I had to bring it down.
Yeah, you take the power, you bring it down, right? All right, so then from there, we can finish this off because we know we have our x minus a, that's our variable part, and then we have to lose a power. So instead of n minus 1 or n minus 2, it's n minus 3, okay? So that's just sort of an overview of like, instead of having to take a derivative for every single one, let's kind of zoom out, be able to think in bigger patterns, even if we see a lot of variable looking things, being able to recognize what's a constant and how do I apply rules that I know you guys know really well. Like I know you know the power rule. So this is just an extension of saying like, let's maybe like dress it up a little bit, make it a little bit fancier, but we're still using the same ideas, okay? And this is really the kind of thinking, not necessarily the topic, but the kind of thinking that you'll start to encounter in like discrete math or linear algebra or differential equations. It's less, it is like computational, but it's also like really big on the concept pieces, okay? Okay, so let's take a look at the integral of a power series. And we're only going to do one integral here, but you should know if you are moving on to take Calc 3 that just like we have first derivatives and second derivatives and third derivatives, you're going to be doing like single integrals, double integrals, triple integrals. So some of your problems in Calc 3 are going to look like this, and then you'll have some function that you're taking an integral of, okay? So you're gonna start to see more than one integral, just like we can have more than one derivative.
I always wondered what they're doing when there's more.
Right,
More
I
of
know.
those.
It's kind of like those composition problems when you were like, oh, well, if you have f of x and g of x, and then you put like a number in here, and then that number goes into the f function. With the multiple derivatives, you do the same thing. You kind of work with the innermost integral, and you kind of work your way out, and you just keep taking the integrals of the new thing until you get to the end. Fun,
That
right?
makes sense.
Like
Yeah.
All right, so integrals of power series. Let's say now I have my f of x, so let me write that out like I did last time, okay? And we know we started with n equals 0 to infinity of c sub n x minus a to the n, right? So that was sort of our integral, or sorry, that was our power series. Now, if I wanted to find the integral of f of x dx, that would mean I need to take the integral of the other side as well. So the integral of the sum of my c sub n x minus a to the n dx. Now, one neat thing we can do is we can actually switch the order of this. So we're going to pull the series out to the front, and then we're going to integrate that c sub n x minus a to the n, okay? So the integral of f of x dx is going to be the sum of the integral of c sub n x minus a to the n dx. All right, so even though this looks probably really complicated and the last thing your brain wants to do on a Wednesday morning. Let's keep in mind what are constants and what are variables, right? So the constants that I have here, I have a whole bunch of them. The only thing I'm really trying to take the integral of here is the expression x minus a to the power of n. So just like you guys knew that the derivative of x to the n was n x to the n minus 1, right? We just bring the power down, we lose a power. How can we express the integral of x to the n, like in a general form?
X minus a to n squared over 2.
Just x to the n.
X to the n plus 1 over n plus 1.
Yeah, x to the add a power over that power, right? And we don't want to forget, if we don't have bounds, we need that constant of integration, okay? And so what we're going to do here is apply that same idea, and same thing with the constants, right? Anytime we've seen constants this whole summer session, we've gotten so good at factoring out that constant, so we really didn't have to worry about it, okay? And so what we have here is that we can take the sum of the integral, which just becomes c sub n, c sub n, and I'm going to have x minus a to the n plus 1 over n plus 1, okay? And then I want to make sure that I have that plus c. Now, most texts will have the plus c in the front, so c plus your series, okay? The reason is, especially if you're looking at an infinite series, sometimes if you have a plus c at the end, it kind of gets lost. So folks will sort of move the constant to the front so they don't forget about it, and then have their series representation afterwards, okay? So this right here is just sort of a little summary piece on what we have when we have a power series, and then we take a derivative or we take an integral, okay? And one thing to note here, right? So this is what I was just talking about. They moved the c to the front, but it's because you had the plus c from your integral and they just didn't want it to get lost in the notation, so they moved it to the front, okay? A couple other things to maybe recognize, that the index changes for the derivative, but the index does not change for the integral, okay? And these also have a radius of convergence that is equivalent to the original radius of convergence, right? Cool. So again, I know I've been kind of saying like, well, you're not really going to use this again unless you're going in a very specific direction, but I think it's kind of cool to like sit here at the end of a summer when you've worked so hard and still be able to look at something like this, that I feel like if we had seen this the first day of class or the first week, you would have been like, what are we doing? Let me maybe drop this class. But look at how far you've come. Like, we're having these pretty big discussions about not just like, oh, I know the power rule, but like I can apply it to the power rule of like a whole lot of things that all follow the same pattern. Or I'm getting ready to get the point where I can take not just one integral, but two integrals. Like, that's a lot of growth right there, and that's pretty cool. All right, so we've got two last examples to finish off our lesson here, okay? So we're going to find a power series representation for f of x equals 1 over 1 minus x squared and determine its radius of convergence. And then secondly, we're going to find a power series representation for f of x equals the natural log of 5 minus x and determine its radius of convergence, okay? And so one thing you might notice is that neither of these look very much like 1 over 1 minus something. There's like too many other things that are going on. So for example, in example number 5, I have 1 minus something, but then it's squared, which makes it totally different from 1 minus something, okay? And then if I look at example number 6, I've got a natural log. I don't even have a 1 over 1 minus something, like not even in the least bit. It's a natural log, totally different function, okay? But here's one of the reasons that it's so helpful to really know your derivatives and your integrals well, okay? So we've got our f of x equals 1 over 1 minus x squared, right? That's the function that we were given. Now, we can rewrite this as 1 minus x to the negative 2 power, okay? And one of the more common derivatives that we've seen this summer, okay, and that I hope your Calc 1 teacher spent a lot of time with you with, is the negative power derivative, okay? So as sort of a separate question, but not really, what is the derivative of, well, I don't know, 1 over 1 minus x? Okay. So if I want to find that derivative, what rule do I need to use?
Quotient.
You could
Power.
use quotient rule, power rule. So we've got a few different options here. You could also use chain rule, but let's set up our quotient rule and kind of see what that gives us. So u would be 1, du would equal 0. V equals 1 minus x, and dv equals negative 1, right? And so when we plug all of those into the quotient rule, we get v times du minus u times dv all over v squared. Now this goes to 0. And so what I end up with is 1 over 1 minus x squared. Okay. So I take the derivative of 1 over 1 minus x, and I get the function that I'm looking for, okay? So this and this are the same. So here's the good news. We know the power series representation for 1 over 1 minus x, meaning I know the power series representation of that. So we can combine that power series representation with this new rule that we have about how we find the derivative and use that to find our power series representation for this new function, okay? So here's what that looks like. We've got our original function. Let's go back to the original function, and that's 1 over 1 minus x squared. Now, based off of the work we did in the blue, we know that's the same as the derivative of 1 over 1 minus x, okay? And so that means it's the derivative of my power series representation, 0 to infinity of x to the n, okay? So if I want to find the derivative of that, that's going to be shift my index to 1, right? Because when I take the derivative of that very first constant, the c sub 0, it's going to go away to infinity because it's an infinite series. I'm going to bring the power down, x to the Lula power. Okay. This is my power series representation for 1 over 1 minus x squared. Now, we did also learn that the radius of convergence for the derivative is going to be the same as the radius of convergence for the original, okay? And so since we know that this has a radius of convergence equal to 1, the radius of convergence for our derivative 1 is also 1. And if you wanted to say, hey, the interval of convergence, you could say that the absolute value of x has to be less than 1. Okay. So pretty cool application of saying, I know these derivatives, and so I can put that together with, again, we go back to this 1 over 1 minus something. It's so helpful because it's not only going to help us find a variety of power series that we saw earlier, but we can now extend it to apply to power series of derivative, okay? All right, any questions on number 5? All right.
Yeah, I have one question. Your original function is 1 over 1 minus x squared. And then you chose to take the derivative of the 1 over 1 minus x just because that is our general equation for the sum of the geometric formula. And then when you took that, it came out to match the other one, which means that you were able to use that and set it equal to your summation of the x to the n, because that would be the power series representation of 1 over 1 minus x.
Yeah, so it's more, I didn't just pick 1 over 1 minus x because it was the one we knew, because there eventually you're going to know a bunch of different ones. And so this is the only one we know at this point. So
Okay.
it's kind of our go-to, okay? But really the connection I want us to see here is that if you have a function that is not of the form of something you know, it might be the form of the derivative of something you know.
Okay.
Or it might be, as we're going to see in example 6, it might be the integral of something you know. All right?
Okay, so we just chose the 1 over 1 minus x just because that's what we're dealing with in today's lesson.
Yeah, yeah.
Okay. Sorry, this is a big plate of food.
Yeah. All right. So Jorge, will you always get the original function when you take the derivative? So kind of the same question. No, not necessarily. You won't always get 1 over 1 minus x, but in the scope of our class, I think it's a good thing to look for. Okay. So that is sort of the one thing we know right now, but I know that in the future that might get more things added on to it, more choices. All right, so let's take a look at this last example here, all right? We've got find a power series representation for, you're welcome, for f of x equals the natural log of 5 minus x and determine its radius of convergence, okay? So again, because we know the 1 over 1 minus something, it's kind of nice to think about, like, how can I relate this, the function I'm given, to something I know, which happens to be 1 over 1 minus something? Yeah, and so if we say, here's our original function, natural log of 5 minus x, okay? Let's see instead of saying, what if I take a derivative of a random function? Will I get the one I'm looking for? This time, let's take a derivative of a random function and see if I can't get back to that. So what might I want to integrate to get natural log of 5 minus x?
Natural log of 1 minus x. I mean, like ln.
1 over 5 minus x?
Yeah, if I take an integral of a natural log, I'm not going to get a natural log, right? But the one rule we do want to remember, this is the one exception to the power rule. But if I have 1 over 5 minus x, oh, hey, we saw that one already today. 1 over 5 minus x dx. That gives us almost our function, except it's actually going to be a negative. Where did that negative sign come from?
Negative x on the denominator.
Chain rule?
Yeah, that negative x in the denominator, and not chain rule, but u sub, right? Because we're taking integrals. So if we have this integral right here, we know that this is pretty close to our function, okay? Now, the nice thing is we already did this one today, 1 over 5 minus x. So what we can say is that our f of x, okay, is equal to the negative integral of the sum of what we got earlier. And I think we got that as x to the n over 5 to the n plus 1, okay? Now, I just want to point out for a moment, you might be looking at your notes being like, I swore it was x to the n plus 1 and not just an n. But let's go back for a moment because this is 1 over 5 minus x, okay? Earlier, we had x over 5 minus x. I don't have the x in the numerator, so when I bump my front terms back in, I only have a 5 to bump back in. I do not have an x to bump in. So the x stays with an exponent of n, while the 5 now has an exponent of n plus 1. Okay. So that's why the powers are different here, because it's almost the same as what we had, but not quite. So what can we do from here? Well, we can say, I know with an integral that I'm going to end up with that constant, right? We put the constant in the front so we don't lose it in the back accidentally. I'm going to have a minus sign here now because there's a minus sign in the front of the integral. And if I use the integral rule, I'm going to end up with the sum. I do not change my index, but my power for x is now going to be what?
N plus 1.
Yeah, I got to raise the power because I'm integrating, but that n plus 1 I also get in the denominator because, oh, that's not taking anymore. Okay, sorry about that. So we've got our x to the n plus 1, and then we have the n plus 1 on the bottom because that's our power rule. But that 5 to the n plus 1 has to stay because that's part of the constant or that coefficient that we have there, okay? Now, this is, we could say, like sort of a general solution, right? Because we just have a random c. But if you wanted to find a particular solution, you can plug in any value of x, and that will give you a value for c. Now, I'm going to pick a value that I think is really nice and easy. So I'm going to plug in 0 for my x. Okay, you can pick anything you want. I'm going to pick 0 here. So what does that give me is I need both sides of my equal sign now. Okay, so I have natural log of 5 minus x equals c minus this summation of x to the n plus 1 over n plus 1 to the 5n plus 1. So I'm going to plug in 0 for x. That's going to give me natural log of 5 on the left-hand side. C minus, what's that going to give me when I plug in x equals 0 here?
0.
That's going to give me 0. So I get c minus 0. That means c equals the natural log of 5. And so as sort of a particular solution, I can write natural log of 5 minus that whole sum, my power series representation, okay? And in this case, what was our radius of convergence when we found this earlier?
X over 5.
5.
Yeah, x over 5 is what was less than 1, but that means that x has to be less than 5. Okay. So 5 would be our radius of convergence. X is less than 5 would give us our interval of convergence. Okay. So just to, sort of whet your appetite, make you perhaps more or less excited for future math classes. But the bottom of the summation of all of this is just that there's so much more out there to learn, and any work that you put into understanding derivatives and integrals definitely are still useful. There's just so many more applications to it other than like just find the derivative and just find the integral. Okay. Folks, that wraps up our lesson for today, as well as our lesson for the summer. I'm going to go ahead and stop sharing my screen here, unless there's anybody who has a question about anything that we've covered in the lesson, or needs to see anything again. Okay. All right, so folks, that is it. I do want to say that it has overall been a really great experience working with you folks. There were quite a few of us in this class, and most of us made it to the finish line, and I'm incredibly proud of you for that, because this is not an easy class in general, and in a summer school class, and coming off of a spring semester like you all had. I know it's not easy, but you've all stepped up to the plate and done a lot of hard work. So congratulations to you on getting super, super close to the end, and hopefully tomorrow with that final exam, we'll put as many of us over that passing line as possible, okay?
I do have a question about when do you think our final grades will become available?
I should have them by Monday.
Thank you.
I have a question.
What's up?
Will you be teaching any like next semester, or maybe the following semester?